Now we're going to go over a bunch of examples of what I've called iterated algorithms, flowcharts that describe a process that repeats itself some number of times. An iterated algorithm performs a task a certain number of times, but the number of times is something that depends on the input of the user. So what it needs is a way to adjust its own structure based on the input. The most common way to accomplish that is with a counter, some sort of variable that tracks the number of times a task has been performed, and once it's been performed enough times, signals the algorithm to stop. So the variable, which is typically not ever going to be output or seen by the user at all, starts at 0 because you haven't done anything yet. Every time you perform the task, you also increase the counter by 1. And then at some point, there's a decision node to check, have you done the task enough times? So here's an algorithm that inputs a natural number n, then it outputs every single number up to that one. So here we have it. Okay, so observe what happens. We start and we input a natural number. The counter is I, and it is declared to begin at a value of 0. You output that, and then you ask, is I equal to n? N was where I wanted to stop counting. Have I reached the value of output where I want to stop counting? If so, stop. But if not, increase the counter by 1, output the new value, and ask again. So for example, suppose we start and then input n equals 2. The next thing we do is we declare I to be 0, and we output 0. I then move to this decision node and I ask, is 0 equal to 2? No, it's not, so I follow the false arrow. So I increase I by 1. So notice that now I has the value 1. So I come here and I output 1. Then I go to the decision node and I ask, is 1 equal to 2? No, it's not. So I come here and I increase the value by 1. So now I is 2, so I output 2. Then I come here and I ask, is 2 equal to 2? Yes, it is. So I stop. As far as the user is concerned, what did they see? They said, okay, I have to input this. Then they see the number 0, they see the number 1, they see the number 2, and then they see that it has finished. So based on the input of 2, we produced an output of 0, 1, 2. This little loop here just says output the number, have I done enough? If not, increase by 1 and output that and check again. So if I input n as 10, I'd start at 0 and I'd go output 0. Is 0 10? No. Now I have 1. Output 1. Is 1 10? No. Increase to 2. Output 2. Is 2 equal to 10? No. Notice that I'm just going to keep going around and around and around. But I'm guaranteed to stop at some point. The input had to be a natural number. I starts at 0 and keeps adding 1. Eventually, it's going to reach whatever the value here was. Now, we do see the importance of the input being the correct data type. If the user was allowed to input, for example, a negative number, if I input -1, I start at 0, and I keep increasing by 1, I'm never going to reach the value I wanted. So it's quite important in this algorithm to start with a natural number to make sure that this really will eventually stop. What algorithms start or finish is not really something we're going to focus on. They're always going to be designed to actually properly stop. Okay, so if I can implement a simple counter, that informs how I'm going to construct addition of two natural numbers. What we're going to do is we're going to add 1 to the number a, because that's something we can already do. But how many times are we going to do it? We're going to do it exactly a total of b times. If I take a and I add 1 to it a total of b times, we have actually computed a plus b. So here's our algorithm. We start and then we input two numbers a and b. Here's our counter. It represents how many times have I added 1 to a. If I have added 1 to a b times, then I get to output whatever my current value of a is and stop. If I haven't added 1 enough, then I add 1 to a and I also add 1 to I. So for example, let's compute 3 plus 2. So we start, we input a as 3 and b as 2. We declare I to be equal to 0. Is 0 equal to 2? No, it is not. So increase a by 1 and increase I by 1. So now a is 4 and I is 1. Come back here. Is 1 equal to 2? No, it's not. So increase a by 1, so now it is 5, and also increase I by 1, so now it is 2. Is 2 equal to 2? Yes, it is. Output the current value of a, which is now 5, and stop. So every time I add 1 to a, I add 1 to my counter. Once my counter reaches the desired number of times to add 1 to a, that's when I know to stop. With this algorithm in hand, however, I can now add any two natural numbers together. It didn't really matter what a was. I could make that any natural number, and it also doesn't matter what b is, because eventually my counter is going to start at 0 and increase by 1 until it reaches that value. This is always going to stop, and it's always going to produce the correct sum, which means I can now simply declare that adding two natural numbers is something I can do as a single computation. So anytime we have two natural numbers, go ahead and add them together as a single computation node rather than replicating this entire structure. But remember, the only computation we started with was adding 1. And we've now managed to use that single, very simple operation to build up something a little more complicated, add any two numbers together. Well, what about multiplication? Now that I can iterate adding 1 to get any addition I want, I can iterate adding some other number to get multiplication. Here's how we do it. Input two numbers, and the goal is going to be to output the sum. I is going to be our counter. How many times have I added a to itself? I start with 0, and if I have added a to itself 0 times, I haven't done anything yet. I have a value of 0. Anytime my counter isn't big enough, increase the counter by 1 and add a to your temporary result. Once you have added a total of b times, output the value and stop. Okay? It's important to start with this new variable x that starts at 0. Because if b happens to be equal to 0, it doesn't matter what a is. The product of a times 0 should be 0. So if your counter has already reached its desired amount because b was equal to 0, you want your output to start at a value of 0. Otherwise, keep adding a over and over again. Let's test it out by computing 4 times 3. So we start, we input a is 4 and b is 3. We declare I is 0 and x is 0. Then I ask, is 0 equal to 3? No, that's false. So increase x by 4, because that's a, increase I by 1. So now x is 4 and I is 1. Is 1 equal to 3? No, it's not. Increase x by 4 and increase I by 1. Is 2 equal to 3? No, it's not. Increase x by 4, increase I by 1. Is 3 equal to 3? Yes, it is. Well, where is the value of x currently sitting? 12. It was 0, but I added 4 to it, then I added 4 to it, then I added 4 to it. It's now at 12. And then stop. So now that we have an algorithm that uses the fact that we can add two numbers together, notice right here, I called upon x plus a. Before the previous slide, I wasn't allowed to do this because up until the previous slide, the only thing we could do was add 1. But the previous algorithm said you can add any two numbers. So I'm using that. I'm adding x and a, even though I don't necessarily know what these are. But now that I can iterate adding a to get out multiplication, I'm going to allow us to call a times b as a single computation, even though we only started being able to add 1. From adding 1, we were able to add any two numbers. And from adding any two numbers, now we can actually multiply any two numbers. So hopefully we're beginning to see that from very humble beginnings, by being able to call upon existing algorithms as steps within other ones, we're building up much more complicated operations. For example, exponentiation. We can iterate multiplication to get exponentiation. We have to be a little careful because 0 to the 0 is not defined, so we're not going to allow the base and the exponent to both be 0. So we just put that as a condition on our input. Input two natural numbers, not both 0. start with I equals 0. This is how many times I've done the multiplication, and I haven't done it at all yet. X is going to be our variable that tracks the repeated multiplication. No addition counted as 0 starting point, but no multiplication, you start with the identity element there, which is 1. How many times have I multiplied? Am I done? If so, output and stop. Notice that if the exponent is 0, b is going to represent the exponent here. If it's 0, I'm never going to see this at all. I'm just going to output x, which starts at 1. So this accounts for the fact that anything to the 0 is equal to 1, except for 0 to the 0, because I wasn't allowed to make them both 0. If, however, my exponent is larger than 0, I'm going to have to start doing this, which says increase the counter by 1 and multiply x by a. So x is just going to keep multiplying a by itself over and over again until you've done it enough times, and then you output that value. It's basically the same structure as multiplication. The only thing that's changed, in the multiplication algorithm at this step, it was x plus a, and here it's x times a. Instead of iterating addition to get multiplication, we are iterating multiplication to get exponentiation. And our starting value starts at 1 rather than 0. And what we're really starting with is the identity value for the relevant operation. When we were doing addition over and over again, we start with the identity element for addition, which is 0. Now that we're doing multiplication over and over again, we start with the identity element for multiplication, which is 1. Now what you should be able to do is check if you start with a is 3 and b is 4, this does correctly output 3 to the 4th is 81. So I recommend pausing the video and trying to do this flowchart. Let a be 3, let b be 4, and really go through and check step by step and do all of the relevant computations until you finally get an output and see that it's actually 81. Well, hopefully you pause for a moment to check that. As we've done before, now that this algorithm is seen to work, we're going to allow it as a single computation. As long as they're both natural numbers and they're not both 0, just go ahead and compute exponentials as a single step. Another algorithm that's commonly developed iteratively is computing factorials. So remember, n factorial is the product of all positive integers up to and including n. Also, 0 factorial is 1. So here is an algorithm that iteratively computes factorials by successively multiplying over and over again. Here we have it. Okay. So try to run through this algorithm to compute 4 factorial. That would be inputting n is equal to 4. But also compute 0 factorial and make sure that you do in fact get out 1 and not 0. So again, pause here, work through it, get familiar with how these things go. Well, hopefully you paused. Now that we have this functional algorithm to compute factorials, we're going to go ahead and allow n factorial as a single computation. Okay, so again, building more and more complicated operations that can now be called upon as a single step. All of the algorithms we've talked about and developed always relied on the inputs being natural numbers, in other words, not negative. Of course, we'd like to be able to add, subtract, etc., and work with negative numbers. The existing algorithms aren't quite going to work. This counter starts at 0 and counts up until some target value is reached. If that target value is negative, you're never going to equal it, and the algorithm will never stop. So negative inputs would kind of break the algorithms we have. In the real world, actual electronic circuits store natural numbers. It's a basis of which sort of circuits are charged or not. But what they do is they store a pair of numbers. The first is any natural number, and the second is either 0 or 1, which simply tells the computer, is this supposed to be positive or is it supposed to be negative? In other words, there's a single bit that stores a plus versus a minus sign. We're just going to use the plus and the minus sign for this designation. So 4 comma plus would mean the number 4, the positive version, and 4 comma minus would mean negative 4, the negative version of 4. These are called signed integers, and you can do kind of operations on them, like, is the negative number a less than or equal to the negative number b? Only if the positive number a is bigger than or equal to the positive number b. And from there, with these sort of rules about how our existing decision nodes would work on signed integers, you can work around arbitrary addition, multiplication, etc. Exponentiation is still a bit tricky. We want the exponent to not be negative because we don't want to work with non-integer values at this point. But from this point forward, we're not really going to bother developing signed integer versions of all of our algorithms. It's a bit too technical, it gets confusing, and it's not really the point. This is not a computer science class fundamentally. Okay? Just assume that we've gone through and done that. We can do sums, difference, and products with any integers. Quotients are still off limits because we do want to distinguish when numbers are whole numbers versus not. And I don't want to work with things like 2 over 5 yet. 10 over 5 would be fine because that's actually a whole number. But because of that distinction, we don't want to work with quotients and division. But addition, subtraction, multiplication of any integers that all totally going to be fine, and we're going to work with that pretty freely from this point forward. So moving on, now that we can work with integers, including multiplication, inequalities, all of that, it's going to be useful to be able to talk about absolute value. Here's an algorithm for computing the absolute value of an integer. So for example, compute the absolute value of 3. Well, we start at the start node as always, then we input 3. 3 is bigger than or equal to 0? Yes, it is. That's true. So output n, which was 3, and stop. Pretty straightforward. I input 3, and I got out its absolute value, 3. What if I want to compute the absolute value of negative 3? Okay, so I start. I input an integer, negative 3. Negative 3 bigger than or equal to 0 is false. So replace n with negative 1 times itself. What's negative 1 times negative 3? It's 3, so that's what I output, and then I stop. So I input negative 3, and I still output the absolute value, 3. So this will always work. If n is bigger than or equal to 0, you don't change it. If n is not, then it must have been negative. But now when I multiply it by negative 1 and replace it, I now have the positive version, and I output that. That's the absolute value function in a nutshell, and as expected, now we're simply allowed to call upon it whenever we want with our traditional notation, absolute value n. So from humble beginnings of just adding 1, and slightly brushing under the rug how we work with signed integers, we can now call upon traditional arithmetic at any point by doing addition, subtraction, absolute values, exponentiation, as long as we're dealing with whole numbers. Okay, so we're never going to raise to a negative exponent, and we don't allow for 0 to the 0. Again, just to stress, we have not developed division because we want to make sure that all of our values are always whole numbers, and division might muck that up. But we're going to deal with this later.